Example 5. Use the summation properties and rules to evaluate each series. All right, let's take a look at the series in part A. We are doing the sum from I equals 1 to 50, and the expression that determines each term in the sequence is 12. Okay, so notice here that I is the index of summation, but the expression that determines each term in the sequence does not have an I. So what that means is every term in the sequence is just a constant, okay? So here we're adding up the first 50 terms of the sequence. So basically the first term is going to be this constant 12. The second term is also going to be 12. The third term is also going to be 12, and so on, okay? And we're adding all the way up to the 50th term. The 50th term is also going to be 12, okay? So we are adding all of these guys up, okay? So basically, if you count your terms, we have 1, 2, 3, all the way up to 50. So we have added 12 up 50 times, okay? So what you have to do here, if you're adding up 12 50 times, that's the same thing as 12 times 50, okay? Go to your calculator, okay, so 12 times 50, the series converges to 600, okay? That's the answer here, okay? This was that property back on page 6, the summation property, the first summation property, that if you are basically summing up from I equals 1 to n, and each term in the sequence is just a constant, all the terms in the sequence are the same number, then all you have to do is n, which is the upper limit of summation, multiply that n value by the constant itself. Okay, that's exactly what we did here. Okay, so that's it. This sequence, and again, I want to keep using that terminology of convergence. This series converges. It's finite. We can add it up. This series converges to the number 600. It adds up to 600. Okay. All right. Moving on to part B. Okay. We're adding up from I equals 1 to 35, and the sequence, the numbers in the sequence are determined by this expression, 3i. Okay. Now, you can certainly write out each term. Okay. There's going to be 35 different terms. So you could figure out each term and then add them all up. But that's a pain because the upper limit of summation is so high. It's 35. Okay. That's just going to be really tedious. So you can do that. Okay. But I'm going to try to apply a shortcut here. Okay. So basically what I'm going to do when I look at this, okay, each term in the sequence here, the sequence is defined by the expression 3i. Each term is multiplied by 3, okay? So we learned, one of the properties that we learned, the second property, was if each of the numbers in your sequence is multiplied by the same constant, you can yank that constant out front. So that's what I'm going to do here. I'm going to take the 3 and I'm going to bring it outside of the summation notation. Okay, so this is going to be 3 times the summation from I equals 1 to 35, but I've already taken the 3 out. That's going to leave me with I. Okay, so that's going to be the first shortcut that I use. Okay, so what I've been left with is 3 times this summation. So I need to figure out what the series converges to. Okay, so if you notice, what am I really doing here? Okay, the expression here is just I, and we're plugging in I equals 1, then I equals 2, then I equals 3, and then we're all the way up to 35, and then we're adding all those guys up. Okay, so what's really going on here, this is 3 times if you write out the series, this is going to be 1 plus 2 plus 3 all the way up to 35. So what you're doing is you're adding up the first 35 natural numbers, okay? So we can use the shortcut listed right here where you're adding the first in natural numbers, okay? This first statement in purple, okay? So we're going to use this n times n plus 1 over 2 on the series here, okay? So if I go back, okay, the 3 is just going to hang out front. It's going to come down, okay? So once I figure out what the series converges to, I have to multiply the result by this 3. Okay, so I'm just highlighting it. I'm not doing anything with it right now. It's just coming down. So now I'm going to apply that summation rule to it. Okay, so I'm going to write right here, this is the sum of the first 35 natural numbers. Okay, so you're going to use the property n times n plus 1 divided by 2. Okay, if you go back and see, I'm using this property right here. Okay, all right, so we would just plug into it. Okay, again, the purple 3 is just hanging out right here to add up 1 plus 2 plus 3 all the way up to 35. Plug and chug into n times n plus 1 over 2. And the n value is going to be 35. Okay, because that's the number we're adding up to. Okay, so it's going to be 35 times 35 plus 1 divided by 2. Okay, so this is going to be 3 times 35 times 36, all divided by 2. And that's going to give me the value of this series, what it converges to. Okay, so I'm going to go to my calculator, punch it in. This is going to be 3 times 35 times 36, and then divide this quantity by 2. Okay, the series converges to 1,890. Okay, that's the answer. Okay, and again, we knew going into this that we were going to get an answer. We were going to get a number because this is a finite series. Every finite series converges. So again, this series converges to 1,890. Okay, so these shortcuts really, really help out. Okay, it would have been very tedious to figure out each of the 35 terms individually and then add them all up. Okay, moving on to the series in part C, we are now summing from I equals 1 to 10. The expression used to determine each term in the sequence is 3i squared plus 5. Okay, again, you can sit here and figure out each of the 10 terms individually. 10's not a whole lot of terms. You can figure out each one individually and then add them all up. Okay, I'm going to use the shortcuts here. We should get the same answer either way. Okay, so what I'm going to do here if I'm applying shortcuts, one of the things I learned from the summation properties was that you can distribute the sigma through addition. Okay, so I'm going to go ahead and distribute the sigma. So I'm going to start off by saying, so I'm going to distribute. This is the same thing as the sum from I equals 1 to 10 of 3i squared, okay, plus the sum from I equals 1 to 10 of the quantity 5. So all I did was distribute the sigma through the addition, through the parentheses. Okay, now I'm going to handle each of these guys on their own. Okay, so I'm going to start by working with the summation on the left. Okay, when we look at this, we're summing from I equals 1 to 10. Each term is determined by 3i squared. So each of the terms is multiplied by 3. Okay, so again, we can take this constant and we can yank it out front. Okay, so this is going to be the same thing as 3 times the sum from I equals 1 to 10 of I squared. Okay, I am going to keep working with this summation, and then I will come back and work with the summation on the right. Okay, so the 3 is just going to hang out front. Okay, it's going to get multiplied by the number that the series converges to. Okay, so when you look at what we're summing up squares. Okay, we're actually, when you read this, this is going to be 1 squared plus 2 squared plus 3 squared all the way up to 10 squared. Okay, so I'm actually going to write that out. Okay, so let me leave my 3 here. In parentheses, this is going to be 1 squared plus 2 squared plus 3 squared all the way up to 10 squared. Okay, so this is the sum of the first, or let me put it this way. This is the sum of the squares of the first 10 natural numbers. Okay, and we learned a summation rule for that. Okay, the 3 is going to hang out front, and then we're going to use the shortcut to compute what's in parentheses here. Okay, if we go back to the bottom of page 6, look at the middle statement here. Okay, if we're adding the squares of the first n natural numbers, we need to use this formula boxed in blue. Okay, so it's going to be n times n plus 1 times 2n plus 1 all divided by 6. N is going to be the upper limit of summation here, so that's going to be 10. Okay, so I'm going to come back over here. The formula is n times n plus 1 times 2n plus 1 divided by 6. Okay, so let me double check that. Yes. Okay, so we're going to be plugging into this. We're using n equals 10. Okay, so again, this 3 is just coming down. Okay, now apply the summation rule here. Okay, plug into n times n plus 1 times 2n plus 1 over 6. So we're going to get 10 times 10 plus 1 times 2 times 10 plus 1, and then everything is going to be divided by 6. Okay, so we can simplify here. This is going to be 3 times 10 times 11 times 21 all divided by 6. Okay, and then let's see here. I'm leaving some room because I still have to compute that other summation. Okay, I will go ahead and figure out what this is. This is going to be 3 times 10 times 11 times 21 divided by 6. Okay, that turns into 1,155. Okay, so that's what the first series converges to. All right, so now I need to go back and handle this particular series right here, the sum from I equals 1 to 10 of the quantity 5. I'm going to go ahead and rewrite this in a different color so you can kind of see what comes from where. Okay, so here we go. All right, so here we are just adding a constant. Okay, you're adding from I equals 1 to 10, but the quantity, each term of the sequence is made up of a constant. Okay, so what we're doing here, this green series, we're just adding 5 to itself 10 times. Okay, so that's what's going on here. Okay, so the shortcut for this, which I'll continue to just write step by step here, the easiest way to compute this, okay, if we write it out, we see that we're multiplying 5 by itself 10 times, so we just need to do 10 times 5, which is going to be 50. Okay, so the green series converges to 50. Okay, add that to the result of the blue series, okay, to get the final answer. Okay, so the overall series, the series that we started with, okay, this guy right here, okay, converges to 1,205. Okay, so I'll write that one right here. This is the answer. Okay, so I'll write down here, the series converges to 1,205. Okay, this involved a lot of shortcuts. It may have actually been faster here to just take each expression or each I value, so from I equals 1 to I equals 10, plug and chug into this blue expression, come up with the 10 individual terms, sum them up, and get the 1,205. Okay, you kind of just have to weigh each problem and figure out what the quickest approach will be. Okay, but again, if you did plug and chug and compute each term individually and then add them all up, you should get the same value, 1,205. Okay. All right, let's try part D. Okay. Part D. Okay. In actuality, we're only doing 5 terms here, so after what we just saw in part C, it's probably going to be easier to just compute the terms individually, add them all up. You can always double check with the summation formulas. So I'm going to start by letting I equal 1 here. Okay, I'm going to plug into my expression. So the first term of the sequence here is going to be 1 cubed plus 2 times 1 minus 8. That's going to be 1 plus 2 minus 8. That's going to be 3 minus 8. That's going to be negative 5. And then if I equals 2, plug that in. So we're going to get 2 cubed plus 2 times 2 minus 8. This is going to be 8 plus 4 minus 8. That's just 4. And then I equals 3. This is going to be 3 cubed plus 2 times 3 minus 8. This is going to be 27 plus 6 minus 8. And so let's see, this answer is going to be what? This is going to be 27 plus 6, 27 plus 6 minus 8. Okay, this will give us 25. All right, a couple more terms here. So if I is 4, we're going to get 4 cubed plus 2 times 4 minus 8. Okay, so this is going to be 64 plus 8 minus 8. That's 64. Last term, I equals 5. That's going to be 5 cubed plus 2 times 5 minus 8. That's 125 plus 10, which is 135 minus 8. That's going to be 127. And then if we want the summation here, if we want the value that the series converges to, we just need to add these guys up. Okay, so this is going to be negative 5 plus 4 plus 25 plus 64 plus 127. Okay, so let's add that up. This is going to be negative 5 plus 4 plus 25, 64, and 127. Okay, so if we add all this up, the series here converges to 215. Okay, so this was computing the series by examining each term in the sequence individually and then just adding them up. Okay, again, you could go to this, go after this number by applying the summation rules and properties. Okay, if we did that instead, okay, I'll write that up here. We could have started by distributing the summation symbol, so distribute the sigma. So we get the sum from I equals 1 to 5 of I cubed plus 2 times the sum, whoops, hold on, I skipped a step. So plus the sum from I equals 1 to 5 of 2i minus the sum from I equals 1 to 5 of 8. Okay, remember the subtraction sign is right here. Okay. All right, so we know that we can distribute a sigma through addition and subtraction. Okay. The next thing I can do here is pull this 2 in front. Okay. So we can do that. So if we write this out, let me just write this in the next step, and then we can just start plugging and chugging. Okay, so pull that 2 out of that middle summation. Okay, that's just going to leave you with I. Okay. All right. This last summation where you're adding from I equals 1 to 5 and you're adding a constant. Okay. So remember what you're doing here. You're adding 8 up 5 times. First term, second term, third term, fourth term, fifth term. Okay. So really you're just computing 8 times 5 here. Okay. So let's do this. Okay. Let's go to the first summation here. Okay. We're summing up cubes. So if you go to the bottom of page 6, we need to use this formula. Okay. We're summing the first n many cubes. Okay. So we're going to use n squared times n plus 1 squared all over 4. Okay. So let's pop that in. We need to be using n. I've already forgotten the formula. I need to memorize it. It's n squared times, n squared times n plus 1 squared all divided by 4. Okay, so that's what we're going to use to compute this yellow sum. Okay, and n is the upper limit of summation, so it's going to be 5. So this is going to be 5 squared plus, 5 squared times 5 plus 1 squared divided by 4. Okay, and so that is going to give us, let's see if we put this in the calculator, 5 squared times 5 plus 1 squared divided by 4. We're going to get 225 from that first summation. Okay, so remember this is all the yellow stuff. All right, so now let's see, I'll use green here for the second sigma. Okay, so I'm going to continue where I left off. I'm going to add, the 2 is hanging out front. So now I'm adding the first 5 counting numbers. So basically 1, 2, 3, 4, 5. Okay, you don't really need a shortcut here, but I will go ahead and use it just for practice. So if we are adding the first 5 counting numbers, we're going to use the first formula here, the n times n plus 1 over 2. So let me write that down. Okay, so we're using n times n plus 1 over 2. N is the upper limit of summation. Again, that's 5. Okay, so this is going to be plus 2 times 5 plus 1 divided by 2. Okay, so if we pop this into the calculator, we're going to get 2 times 5 plus 1 divided by 2. Okay, you're going to get 30. Okay, so we're adding 30. Okay, that's what the green sigma gave us. Okay, and then we have to worry about this last summation. Okay, so again, we've already talked about what it is. You're going to be basically subtracting the result of this series. Okay, so basically we're subtracting 8 plus 8 plus 8 plus 8 plus 8. Okay, which we know is 40. Okay, the shortcut was to take the constant 8 and multiply by the upper limit of summation, which is 5. So basically we're subtracting 40. Okay, so let me color code this. Okay, all right, so to get our final answer, we need to do 225 plus 30 minus 40. And lo and behold, we get 215. Okay, 215 is what we had already gotten by just computing each term individually and then adding them up. Okay, like I said, you can use these shortcuts, but sometimes they're a pain in the butt too. They're not really shortcuts. Okay, so if you find it, easier for you, like if the upper limit of summation isn't that high, like here it was 5, it's probably going to be more efficient to just figure out each term and then add them all up. However, if you see an upper limit of summation like we did in part B, we had 35, or maybe you have 50 like we did in part A, it might be more feasible to use the shortcut route. But either way, you should get the same answer.